Hi everyone, I'm Aaron Greenblatt from IronMill. We're here to talk about zero-knowledge proofs. It seems like there's some industry confusion about how long it takes to generate a ZK proof. At the highest level, there are many types of ZK proofs, each with unique computational requirements. To dive into a bit more detail, we'll be having a conversation with Seve Sisneros, a senior cryptographer at Semiotic Labs, and Neal Kaufman, the CEO of Aligned. Semiotic is a core developer of the graph, and Aligned has deployed several thousand FPGAs to run ZK compute workloads. At IronMill, my company, we build end-to-end deployment tools for ZK systems using special-purpose hardware. During this video, Seve will be walking us through the process of selecting ZK proving algorithms for a project with the graph. After Seve's presentation, Neal, Seve, and I will talk about data-centered deployment of ZK workloads. Before we get started, however, Seve has challenged me to a proof competition. We're going to see who can generate a proof the fastest. Seve has requested a whiteboard, and I have this GPU from NVIDIA, which I'd love to use with Lambda class's new library, LambdaWorks. Let's see what happens.
All right, so the statement we're going to prove is, I know a secret X.
All right, so I'm here. We're going to get some zero-knowledge proofs going. So I brought the GPU that I just showed you earlier, and then I found some more RAM, because I know every time I try to do zero-knowledge proofs, I always run out of memory.
All right, and so X is a number, and like the special thing about X is X comes from something called a field. So you could think of a field as like the normal numbers we typically work with, but the important thing is X is some number from this field.
So let's get these into the box here, and then we can plug her in and get LambdaWorks on here. Really excited.
And so before we start proving, with every proving system, there's always kind of like this public setup, right? So these are all the parameters that go into your proving system. And every proving system has something like this. And it's an important kind of distinguishing feature of different proving systems.
So, so where to begin? Let me get the box open. Seems like a good idea. I guess it's these two screws. They're awful tight. Hey, let me go get some tools. I'll be back.
And so the proving system that we're using, these are kind of the public parameters. These are what both the prover and the verifier kind of agree on. And so the first thing is they pick a field, and this is kind of like the field where the numbers come from. They pick another thing, a special thing called a group. And the trick about this group, it's another kind of like set of numbers. The size of this group must be the same size as F. And then they pick some public element, some public number that comes from this group G that they picked. And then the last thing that they pick is this kind of function, this special function that maps numbers to elements from that group. And so, you take hash of the 1, it maps you to a G1 element. H2, it gives you a G2 element. And then the real secret sauce of this proving system is a function called a pairing. And so we denote a pairing just like with this E, and then it takes in 2 elements as part of the function parameters. And the special thing about this pairing is that it has this property where if you have a number A and multiply it by a number G, and then you plug that number into one part of the pairing, and then you have another number H, plug that into the other part of the pairing, you get this kind of equality. So this number A can kind of float around between the G and sitting on the H. And so this comes in, it's important whenever we start looking at how do we prove that I know this X in F.
All right, I got all the tools. Okay, let's see. We got a wrench and another wrench, and these probably don't help. And hey, this is looking promising. Hey, look at this. Let's see what we can do. Let's see. Hey, this one works. Great. Let me loosen the other one, and then we can get going on these proofs here. I'm really excited. So then this should just slide back, right? Well, it's not. Well, here we go again. Hey, look, anytime you build something, there's always something. This really doesn't open.
And so the first thing that I do as a prover is I take this public element that both the verifier and I know, and I multiply it by my secret number X. And then I send that over to the verifier. And so then the verifier sits here with their number, and all they see is this new number, and we'll call it P. They don't know what x is, they know what g is, and based off the properties of the math underneath, they have no way of knowing what x is given just p. And so now the verifier, not trusting yet that this prover actually knows this x value, they pick a random number, a challenge. And this challenge, it can be kind of any number, just a big number. You can give it like a bunch of coin tosses or something. And so we'll pick a random number, we'll say 7. So they pick the number 7, and they send that over to the prover.
All right. Kinetic energy. Yeah, kinetic energy. Yeah. Okay, let's try it. Okay. Here we go. Hey, all right, that did the trick. We got it open. This is awesome.
So now the prover gets this number 7, and they have this xg. The next thing that the prover does is they calculate h of 7, and that h of 7 gives them another group element. We'll call that g7. And then the prover takes their number x, multiplies x by g7, and they send that back over to the verifier.
We can get the GPU out. That's perfect. Okay, so here's the old GPU. It's full of dust. Let's put in some more horsepower.
And so now the verifier has these two numbers, p and this number p7. Under the hood, they still don't know what x is because they can't get back to x from just this stuff. And so now the verifier wants to know, does the prover actually know, this x value here? And so what they do is they take this pairing and they compute E of this element that they know, G, with this P. So they take this pairing value, and then they check to see if this pairing value is equal to E of P7 G. And now the trick here is if we look at what the properties of this pairing are, we can kind of look under the hood, and we can see, okay, E of G with P, so we know P is this X times G. And we're checking to see, is this equal to E of this P7, which is, this first element here is, they plug in G7 here that they know, this G7 that they know in this first element, and then this P value. And then here they have X of G7 with G. So now, using this trick with this pairing here, we know this value that you multiply by can kind of float around back and forth. So if we look, say, focusing here, we can see that E of X times G7 paired with G is equal to E of G7 X G by the property of this pairing here. And then we can check, lo and behold, this is equal to this, which is equal to this. And so everything checks out, and the verifier accepts. The prover does know some secret value X, such that X times G is equal to P. And the proof is done.
Yeah, we're making good progress here. We got the GPU in the box. We just have to throw Linux on, download LambdaWorks, and then we're going to be off to the races. I wonder how Seve's doing.
And the proof is done.
Cool. So you did a proof already. Seve, I was just checking in with you to see how you were doing. I haven't really gotten my computer turned on yet. I mean, I just got my GPU installed, but you're done already. I mean, well, I thought I had a chance. I mean, eventually we'd want a computer for this. So, so is it true that there's like more complexity and that this is just one case?
Yeah, absolutely, right? So here we're just trying to prove kind of one secret, just one secret number X here. And whenever we think of these proving systems, we're trying to prove a big statement. Like, I know the result of this big computation. And so to be able to get that, you have to have basically, I know a bunch of X's. And in some statements, like, I know a million different X's. So you would think of, we just take this little X times G, we'd have to redo this a million times. And so, I've never done it. I don't know if I could ever do it, but write out X times G a million times. I'd probably lose that race. But yeah, right, so statement sizes, that's it, small statement, easy to prove. You can see it on a whiteboard. These larger statements, much harder to prove. But follow kind of the same idea.
Hello,
I'm Seve Sisneros, a cryptographer at Semiotic Labs. We are core developers for the Graph protocol. And today I am hoping to share some insight from our design process as we're developing a snark-based solution for the Graph. The goal is to demonstrate some of the trade-offs encountered when trying to build a system using snarks. This is an abridged version of a talk I gave at DevCon 6, and you can find the full version on YouTube at the link below. First up, a quick recap of what a snark is. The acronym stands for Succinct, Non-Interactive Argument of Knowledge. Essentially, a snark enables someone to succinctly prove that a statement is true. For example, I know a message M such that the hash of that message equals 0. The catch is that in order for the proving system to be considered a snark, the proof must be shorter and the verification must be cheaper than just trivially sending the message as the proof and having the verifier perform the computation, in this example the hash, on her own. There's another variant out there called the ZK snark. The ZK stands for zero knowledge. In addition to proving succinctness, the ZK snark reveals nothing about the message M. This is especially useful for privacy applications. In this talk, we are only concerned with the succinctness property of snarks. First up, I'm going to describe the system that we are working on. So the Graph is a decentralized blockchain data indexing and querying protocol. In the protocol, indexers organize blockchain data and serve query requests. Being a decentralized protocol, the Graph uses tokenomics to incentivize honest behavior in the network. What that means today is that indexers charge a fee for the queries they serve. In the Graph, there is an entity called a gateway. One of the responsibilities of a gateway is to facilitate query requests and payments. Whenever a gateway makes a query request, they also cryptographically sign a receipt which indicates that they will pay for the request. The receipt consists of a unique ID for the query request and includes a value charged for the query request. Indexer payments are facilitated through smart contracts on a blockchain network. An indexer can send a signed receipt to the smart contract. The smart contract will check that the signature is valid and then transfer the value owed to the indexer. The challenge here is that there can be many query requests. In our case, we consider up to 1 million. It would be far too costly for the indexer to try to send 1 million receipts to the payment smart contract. This is where a snark comes in. Instead of sending all receipts to the smart contract, the indexer stores the signed receipts in a table. We call this a scalar table. The goal then is to use a snark that can prove 3 constraints regarding the receipts stored in the scalar table. 1, that the total value is equal to the sum in the value column. 2, that all signatures are valid. And 3, that all IDs in the ID column are unique, preventing double spends. The snark will then generate a proof that all 3 constraints are met. The indexer can then use this one proof in the on-chain smart contract instead of the 1 million receipts. The smart contract checks that the proof is valid and then unlocks the total value owed to the indexer using a single low-cost smart contract transaction. So what makes this problem interesting? 1, we are using the succinctness property of the snark to compress 1 million signature verifications into a single snark proof verification. In general, when we talk about proving a statement with a snark, we first have to translate that statement into a circuit, which is a system of logical wires and gates. The computation required to prove and verify a statement is related to the number of gates in the circuit used to represent the statement. And so, another interesting point is that the size of the statement we are trying to prove with the snark is very large. Naively, in order to build a monolithic circuit which can verify 1 million signatures would require about 200 million gates. This is at the boundary of what is currently feasible to prove with today's technology. Another, more subtle point is that we are trying to use a snark as a black box in the payment system. For example, we don't want to introduce any additional security assumptions into the system if we don't have to. And finally, on the business side, the proving and verification of the system must be cost efficient, otherwise it degrades the performance of the entire protocol. So, how do we know when we succeed? There are different metrics for quantifying snark performance. We'll use prover time, prover memory, proof size, and verifier compute. We'll use these charts to demonstrate the performance of the SNARK systems we are investigating. On the x-axis, we are essentially showing how many receipts we are trying to verify with our SNARK. On the y-axis, we see how the cost increases as we increase the number of receipts we are verifying. We then use these metrics to estimate the total overhead cost in dollars of using the system. Okay, so where do we start? There are many different types of SNARKs, all with different performance characteristics, trust assumptions, etc. But at a high level, there are two major categories of SNARK: transparent and non-transparent. So the first decision we need to make is to pick between one of these. The distinguishing feature between transparent and non-transparent SNARKs is that non-transparent SNARKs require a separate setup protocol to be run before any proving can be done with a SNARK. This setup needs to be carefully considered as it is critical for the security of the proving system. Essentially, this setup introduces additional security considerations for our overall system. Because we want a black box, we decided to start by looking at transparent SNARKs. So now where do we go? To answer this question, we start by looking at the properties of the statement we are trying to prove with a SNARK. One thing that we notice is that the scalar table is highly structured. We're essentially trying to prove the same statement, that a cryptographic signature is valid, for each row. So the circuit that we would build would look like a series of small, identical circuits. It would be great if we could take advantage of this structure to reduce the computation and communication required for our proving system. Pulling on this thread, we find that there exists a class of SNARKs that do just that. These are called recursive SNARKs. Recursive SNARKs are essentially a SNARK of a SNARK. The key observation to enable a recursive SNARK is that we can create a SNARK that proves its own validity. For proving our table, we essentially create a circuit that proves the validity of a single row, shown here as F, and then augment that circuit with another one, which proves that the SNARK verification of our proving system is valid. Using this new circuit, F prime, we can prove that a particular row's signature is valid and that the SNARK proof for the previous row is also valid. We can continue this for all rows. Accumulating proofs this way means that the proof size and the verifier work is only related to the size of the F prime circuit, not the entire table. There are a few options to choose from in the transparent recursive SNARK space. A couple of the big names are Halo and Nova. We decided to investigate Nova. It has the smallest constant size verifier circuit. It uses another proving system called Spartan, which means that the prover will be very efficient, essentially because it doesn't require computing FFTs. It also uses the Bulletproof's IPA polynomial commitment scheme, which means that it will be a transparent SNARK and have relatively small proof sizes. And also another benefit is that there is an open source implementation available that we can build on top of. Okay, so let's see how much using Nova for proving our scalar table will cost. The first thing that we notice is that prover memory, proof size, and verifier compute are all constant. This is the big benefit of the nature of recursive proving systems. We also see that prover time grows linearly with the number of rows we are trying to prove. If we are trying to prove the full size of our scalar table, it would take about 50 hours. Fortunately for our use case, prover time is not critical. The indexer can afford to wait a couple of days if it means that they will get a big paycheck. The real problem is in the details. Nova requires a mathematical structure called the cycle of elliptic curves, and the current implementation is written to support only one set of curves, called the pasta curves. The problem is that the Ethereum virtual machine only supports one curve, called AltBN128. What this means is that if we wanted to write a smart contract to verify a Nova proof, we would first have to write EVM code to support the operations using pasta curves. These operations are not cheap. We estimated the cost in Ethereum gas of implementing these operations and then verifying a Nova proof. The total gas cost would come out to about 764 million gas, or about $76,000, using the going rate for gas sometime last year.
We could try to modify the Nova system to support Alt-BN 128, but we are looking for mostly off-the-shelf solutions, so we decided to look elsewhere. Now, there's a lot more transparent snarks that we could investigate, and in some cases we did, but there's one snark that seems to be very popular right now. A non-transparent snark called Plonk. Plonk is a very popular proving system and has spurred many follow-on systems which improve performance for certain applications. It uses a universal trusted setup, so the security of the proving system does depend on the security of the setup ceremony, but being a universal setup means this ceremony only has to be run once and the results can be reused for many applications. The big benefit of Plonk is that the proof size and verifier compute are small and constant size, regardless of the statement size you are trying to prove. In our case, this means that the on-chain verification of the scalar table will be very efficient. Additionally, unlike with Nova, the Ethereum virtual machine natively supports operations required for Plonk verification, which is likely one of the reasons why it seems it's being used by everyone developing snark applications for Ethereum. Another nice thing about the popularity of Plonk is that there is a lot of high-quality open source code to build on. So let's see how Plonk fares in our application. The first thing we notice is the small constant size proofs and the cheap verifier computation. The total gas cost of verifying the Plonk proof would come out to about 500,000 gas, several orders of magnitude cheaper than Nova. But it's not all positive. As with all things, there are trade-offs. The Plonk prover is expensive. Plonk requires FFTs to be efficiently computable, which essentially means it will require a lot of memory to prove large statements. In our case, to prove the largest statement we care about, the scalar table with 1 million rows will require about 3.5 terabytes of memory and about 10 hours of total compute time. If we rented a GCP instance to do this, it would cost about $200. So, in addition to the cost of requiring a setup ceremony, we still wouldn't be able to generate a proof for less than $30 using off-the-shelf software and general-purpose compute infrastructure. Though the solution is still significantly cheaper than Nova would be, and if we really wanted, we could probably engineer a solution using Plonk. For our particular application, that's not what we did, but you have to see the full talk to see how we resolve this. This is the end of the technical content that I wanted to briefly cover with this talk. Here are some high-level takeaways. As we saw, there are different types of snark systems. Each system has its own cost and profile and performance trade-offs, and the right snark system will be highly dependent on your application and the resources available. Just a little extra content, we only talked about two snarks, Nova and Plonk. In reality, the space is much bigger, and the trade space is much more complex. Here's just a sampling of what's out there. Thank you for watching. If you have any questions, I always love talking about snarks and cryptography in general, so please reach out. As I said in the beginning, we are Semiotic Labs. In addition to cryptography, we also have expertise in AI and ML and are applying them in the Web3 space. If anything here looks interesting, again, please reach out.
Hello everybody, my name is Neal Kaufman. I'm the Chief Executive Officer of a company called Aligned. Aligned is a company that has a proprietary architecture and technology solution to provide high-performance computing focusing on the manipulation and processing of massive data sets. We're here talking specifically about ZK proofs and the specific part of generating ZK proofs, because in dealing with this industry, people talk and say, I'm going to use a ZK proof to do something and run it on some type of hardware. But there are different types of ZK proofs. There's different utility, there's different flavors and implementations. So I wanted to bring together two really serious experts to address some of these questions about utility, about the different types of ZK proofs, and what it really takes to implement a full ZK proof driven solution. So I have with me two people, they'll introduce themselves, but experts in cryptography, machine language, data centers, protocols, etc. A lot of stuff in two people, but they're really that exceptional. On my left, I have Aaron Greenblatt from IronMill, the chief executive of IronMill, and he'll give himself a quick background, and then I'll introduce Seve Sisneros from Semiotic, and then we'll get started. Aaron?
Neal, thank you for moderating this panel today. It's great to see you again. Some background on myself. My name's Aaron Greenblatt, and I have been starting companies since I've been a teenager. I hold a EE PhD from Stanford, where I studied machine learning systems, in particular quaternion neural networks. We used the quaternion neural nets for applications in time series prediction, prostate cancer imaging, and other areas. After grad school, I went to a hedge fund for a year to lead machine learning efforts, and then came back to Silicon Valley to go be an entrepreneur. My last company was a cybersecurity deal where we were building a zero trust file system working closely with the US Air Force. The idea is we'd watch the behavior on your laptop, and if the behavior started looking unusual or suspicious, we could shut down file system access, so if you had any sensitive data on the machine, that you could still protect the data. About 2 years ago, we switched into blockchain and zero knowledge, and that's my latest company, IronMill. At IronMill, we're building scalable zero knowledge deployment systems. So you can imagine building a zero knowledge app on your computer, but then there's always the challenge of if I have 1 billion users who need to have proofs and need proof generation, or I need to do proof verification on every smartphone on the planet, how do I think about deploying that? What are the scalability challenges? And not only that, but how do you get all of that to work seamlessly so that it's really easy for software developers to come in and build new applications on top of it? So these are the types of things we do at IronMill. And with that, I will hand it to Seve.
I'm Seve Sisneros. I'm a senior cryptographer at Semiotic Labs. I guess my whole career has been kind of in the field of cryptography, right? So I started off, I have a master's degree in mathematical cryptography. I worked at Sandia National Labs as a cybersecurity R&D researcher there. So basically just kind of making and breaking crypto systems for the US government. And then after that, I spent a couple of years at Northrop Grumman, a defense contractor, helping to develop some anti-tamper solutions for their various systems that they deploy. And then for the past couple of years, I've been at Semiotic Labs, kind of working in the Web3 space, in particular helping develop zero knowledge protocol solutions for the Graph protocol.
Awesome. Well, great. Well, first of all, thank you guys for being here, and I really look forward to hearing what you have to say. So maybe I'll start off, Seve, by asking the question, focusing on the utility. Why do zero knowledge proofs exist? What is the benefit that we could be able to expect? What are the usage characteristics of a well-implemented solution using zero knowledge proofs?
So off the top of my head, what I think of why zero knowledge proofs get me excited is there's kind of like two really interesting properties. The first one is kind of this succinctness property of these zero knowledge proving systems. So it's basically a way for you to compress computation is kind of how I think about it, right? So I have this big statement that I want to compute and prove, but I don't have enough compute power to compute it on my own. So I kind of offload it to someone else. They have the big resources to compute this, and then they give me a result. The question is like, now how do I trust that result? Right, so they have all the compute resources. They compute the statement, give me the result. That's where zero knowledge proofs come in. Is in addition to computing the result, they can hand me this proof that the result is valid. So it's a way that I can get a result and trust the solution. The other thing that's really interesting is this kind of zero knowledge piece. So in addition, kind of to computing a result, you can also kind of reveal no additional information other than that statement is correct. So that's where it gets really interesting for like privacy solutions and stuff like that.
Gotcha. So the first one is really talking about outsourcing computing power, leveraging other types of networks to get your work done. And the second one is the zero knowledge allows for privacy and security and novel applications that have been and probably will be developed using zero knowledge proofs.
Absolutely. Yep.
Aaron, just interested in your thoughts as well?
Yeah, I mean, I would echo what Seve's saying, where we live in a world right now where anytime you want to run a big computation, you hand it off to a data center and then you trust that they're going to give you the right answer. When you do this handoff, of course, you hand all your data to them, you hand any sort of service guarantees to them, and then you get a result back and you just hope that it's correct. And I think a lot of people tend to think about incorrect results in sort of a malicious sense, where maybe there's a bad actor tampering with the data or tampering with the processing. But the reality is that with today's hardware, a lot of the applications you're seeing, machine learning, AI, we're moving to like lower and lower precision numbers because we can't do the processing fast enough. So if you're running, we used to run 64-bit double precision floating point, and then it went to 32-bit, then it went to 16, now it's going to 8. And in fact, I saw this during my PhD, that if I ran things in 16-bit precision, I ran into problems. And because, especially with all of these kind of machine learning as a service offerings, you don't know what type of rounding error they're introducing. Mm-hmm. When you get back to proofs of correctness, a zero-knowledge proof that the computation is accurate, it's very helpful because you can have a lot of incorrect results, even if things haven't been intentionally tempered. It could be a rounding error, it could be equipment that's overheating, bits that are randomly flipping. So this is important, and it's something that people don't really talk about.
So you're saying, in addition to the succinctness, which Seve pointed out, there's actually ensuring that it's calculated correctly, whether it's maliciously or unintentionally. There's mistakes, especially with the evolution of technology.
Yeah.
I'd also like just to go and unpack one other thing you talked about. You talked about service levels.
Yes.
So you have a lot of experience in data centers and rolling out hardware. I would imagine that the time to compute a proof matters. And is it easy to compute these proofs? Do people care, like, hey, I could take a week or I could take a day? What's your thoughts from someone who's on the hardware side but also deeply understands the business side, having started Silver Business, about that issue for the utility of ZK proving?
Yeah, I mean, look, so latency matters, and that's always been true. Now, you have to back up and say, well, what's the customer use case for this? So take during grad school, I had machine learning simulations, and they would take a while to run. And I actually thought that was great because I would hit go, and then there's nothing I can do for 4 hours, so I'll go read a paper, I'll go ice skating. It was great. If I'm trying to run a business where I need an answer and I need it sooner than in 4 hours, then 4 hours is a problem. I mean, imagine I'm running like an airline reservation system and you click reserve and 4 hours later you get your plane ticket. Well, clearly that's not what you want. And yet in some of the blockchain protocols, especially in DeFi, you're seeing a lot of click trade, and 4 or 5 hours later, you actually get finality on the result because it's on some sort of ZK rollup or something like that. Now there's also a piece of this. So first there's the application, but then there's also a piece which is within the data center, what service level are you getting? Imagine all sorts of issues. So did I get dispatched to the fastest GPU or the fastest FPGA? Did I get the 3-year-old model that's slower? I worked in a data center once where they had one router for the entire data center because it was sort of a tier 2 facility, and it was lower cost for that reason. But then they had a distributed denial of service attack on the one router with, I think it was 20 terabits of information a second. It was crazy. And so it shut them down, and it shut down the whole data center. So from a system availability standpoint, now my latency just became, first the servers are down, then they have to get back up, now we can start processing. And so there's a bunch of deployment characteristics that matter in addition to just if I had the ideal ZK proof with the ideal algorithm on the ideal hardware. But even in ZK, even that problem still could be a few hours depending on the proof you're doing. And I think as an industry, we'd like to get that down to like maybe a minute or two. That would be awesome.
Well, that's great, because the last part of the whole thing was interesting, but the last part was specifically, depends on the type of ZK proof you're running. So everybody says, I'm running a ZK proof. But my understanding is that there are different types of ZK proofs. So is there any way to sort of characterize, maybe Seve, we'll start with you, because from the fundamental math through the machine implementation, but what types of ZK proofs are there, and what are the different use cases for each one?
Yeah, so whenever I start thinking about ZK proving systems, right, there's kind of like two main categories that I think of, and
like the distinguishing factor, I guess, between these two is kind of like the security assumptions that go into them. And so the two high-level proving systems that I think of, there's transparent snarks, and then there's these trusted setup snarks. And then kind of maybe as a subset of the trusted setup, there's universal setup, so basically there's the setup snarks and then the not setup snarks. And so what makes transparent snarks really interesting is that the proving system, to get the security of the proving system depends only on the underlying math. Like there's no other external protocols that need to be run. It's basically I have my proving system, it's written out, I got the protocol spec, I can just implement it and go. The trusted setup or universal setup snarks require some external process. So it's this trusted setup ceremony that needs to be run, right? And so right now on Ethereum, they've got their big trusted setup ceremony that's been running now for several months and will continue to be running basically to generate the parameters for their proving system, right? So that's kind of like the first two big categories. And then kind of within those, you have different types of proving systems. One that's really interesting is kind of these recursive proving systems, right? So it's a proving system that can kind of prove itself, right? And so you take advantage of this kind of like recursively proving things and chaining things together, and you can get smaller proof sizes for the statements that you're trying to prove. And then from there you start getting into all the details of the underlying math and the architecture, sure. Right? The different polynomial commitment schemes, and so it's a big space.
But broadly, between those two transparent and non-transparent, right? Which one do you see being implemented more now or in the near future? And do you think that's going to change over time as new technology or hardware is invented, or no, you really think this one's going to sort of take the lead because of the utility it delivers?
Yeah. So right now, again, being in the Web3 space, Ethereum's the big blockchain in the Web3 space, and I think actually a lot of the work, I think a lot of the progress that has been made in zero knowledge proving systems has been driven by like applications in the Ethereum space. And so with that being said, like there is one type of proving system that is really efficient to verify on the Ethereum blockchain, and that's these transparent snarks like Plonk, like ROS16. And so what you see is like everybody who's developing a zero knowledge system, they want to get deployed on the Ethereum blockchain, and so they're going to be using a ROS16 or a Plonk based proving system because you get that really efficient verification kind of on chain. That being said, I mean, the space is growing quickly. Like these Plonk and ROS16, I mean, the proving costs are pretty high. They're pretty expensive, so they require like pretty hefty compute resources to prove any statement that's like of interest. Right now, Plonk, ROS16, these ones we see a ton of application, right? Because they're being applied on the Ethereum blockchain because the verifier is cheap. I think there's newer proving systems that are coming out, these transparent proving systems that have, comparably cheap to verify. It's just not it's not cheap to verify on the Ethereum blockchain, right? But as the blockchain space matures, as the Web3 space matures, if people start understanding, what these trade-offs are on the verifier side, maybe you get, precompiled contracts on the Ethereum network that support, your verifier of choice, and all of a sudden, that opens up the door to all kinds of other proving systems. So, I mean, I think it's a pretty dynamic time right now in the space, and I do think that we will see more than just, ROS16, more than Plonk, these types of.
So the question, Aaron, Seve said, ROS16 and Plonk are being implemented because they work on with the Ethereum chain, but also because at one point you said they were cheap, and at another point they said they're very expensive.
Yeah.
So, which it's all relative, right? So, Aaron, I'd love your thoughts, like looking at the ones that are being implemented, Plonk, ROS16, and first, how do you see this in terms of that dynamic within? How expensive is it? How cheap is it? What are the things that people are thinking about? Maybe other systems are even more expensive. Why that's considered cheap?
I think you're getting at this notion of what's cheap, right? And the answer is, it depends, okay? So that's never a satisfying answer, but you need to put your computation in context. So starting with the blockchain context in Ethereum, basically it runs in-order transactions, and a transaction is really just running some code. We call that a smart contract. And the smart contract, it is Turing complete, and people talk a lot about the programmability, but every time you run a single instruction in that Ethereum smart contract, it runs on every Ethereum validator. So think every time you load something from memory, well, if you've got 1,000 validators, now 1,000 machines have to load the same thing from memory. Then you go to add a number, it's 1,000 adds, and so on and so forth. On top of that, Ethereum is a virtual machine, so there's additional overhead there. And then there's even more overhead because you're running a consensus algorithm that everybody needs to come to the same answer and come to consensus on that. So when you put this all together, the Ethereum virtual machine, it does run code. It runs code very, very slowly. And think of it, single-threaded machine, no reorder buffers. So that's something like a 386 or a 486. Once you got to the Intel Pentium, processor architectures had advanced beyond what we see in the EVM. And so now we're talking about zero-knowledge proofs and validating them. Well, what's cheap and what's expensive? Because what's cheap for my smartphone is super expensive on-chain. And what my smartphone thinks is expensive is super cheap if I go to a big data center or a supercomputer. And so the answer is it depends. One of the big things that's exciting about zero-knowledge algorithms, and this is something you can speak to, Seve, is that many of these verifiers are super duper efficient, so you could actually run them on chain. In practice, there tends to be a trade-off between if I want a short proving time on like a super powerful machine, because the proofs are intensive to create even if you've got special purpose hardware like GPUs or FPGAs. If I want a short proving time, the cost tends to be that I get a longer verification time. And that longer verification time may not work on chain, but it'll work great on my laptop. And so, back to what Seve was talking about, there's different proving algorithms. And when you select one, you want to look at, how much verification time can I afford? Based on that, that makes you back into how much proving time am I stuck with? And then you think about where these different components are running.
Gotcha. So the more you spend on the proof generation side of things, the easier it is to verify. Is that a rough way of looking at it? So you can skimp on the proof generation, but then you're going to have a heavier load across these hopefully thousands of decentralized verifiers, for lack of a better word. All right. So taking that to the next level. If somebody's rolling out a protocol or an investor's looking at a chain or someone's like, maybe we'll start with you on this one, Aaron, because of your background in data centers. What are the questions that people need to ask? Like the investors, the operations people, the people designing the protocol itself, the questions they need to ask so that they can create something that can deliver utility but in an economic way. So what do people need to think about as they're trying to roll out at scale a zero-knowledge proof-driven application in utility?
Yeah, so there's a number of things to unpack in that question. I first want to unpack the word value. Okay, so in blockchain, historically, we've seen projects that are good ideas sort of launch a token kind of early, and then the token gets to be worth a lot of money. But typically in a startup, how you measure how well the startup is doing is the customer feedback, it's product adoption, how many million people use your product. And there's been too much measuring just with kind of tokens, right? So step one is, let's build things that people want. Right now, there's a whole round of blockchain infrastructure to be built. And so as you think about delivering value, it should really be the feedbacks from devs who are using the product. Once you've gotten there, if you're building a zero-knowledge product, then you need to think about what am I building and how does it run? So just to kind of back out of this or step out of this for a minute, when you think about cryptography and encryption specifically, the only company to ever make money on encryption as a product was RSA, and the rest of the world used encryption to build really cool products like Gmail or Amazon or whatever. Zero knowledge is going to be similar. You can use it to build really awesome products, but it's not a product in and of itself. So then back to our discussion earlier of sort of, what's cheap, what's expensive. If I'm using zero knowledge, for example, in a privacy application, Maybe I want to go to a website and prove that I'm at least 21 years old. That probably doesn't need a blockchain at all. Things get to run in browser, they get to run on like a big server that hosts the website. So that's going to lead to a certain selection of proving algorithms that can support the compute constraints that I'm dealing with, which in this case are not that constraining. If we want to do a DeFi product on chain, and maybe we want to do something that's like using pricing options off chain and then using ZK to prove that the pricing is legitimate. Well, now I need proofs that verify very, very efficiently because it's happening on chain. And so now that leads to a different set of design criteria.
So Seve, as someone who's worked it from the math side, from the crypto side, right? How often does this come into the conversation? Like in your experience, having developed these and worked with people on the cryptography side or on the protocol side, in your experience, is this something that's almost seen as an afterthought, or is this something that is contemplated up front? And what are the implications for actually rolling that out at scale based on your experience just in dealing with lots of people in this space?
Yeah, so I think, in my experience, I mean, all my experience has been focused primarily at getting blockchain applications, right? So we're working in the Web3 space. We want to get proofs that are cheap to verify on chain. The challenge, so I mean, that becomes kind of like constraint number one, right? It's like if this cannot be cheaply verified on chain, then we can't use it. And then from there, we start, trying to find solutions that can meet our requirements based off of, prover time, proof size, stuff like that. The challenge is, again, it kind of ties back to, maybe it's like a blessing and a curse, right? So Ethereum drove, the excitement for zero-knowledge proofs that was driven by Ethereum drove a ton of research, and it drove a ton of research into improving Groth 16 proofs. It drove, Plonk, it drove Plonk 2, and all, a whole lineage of research, which, I mean, it's great. They're cheaply verifiable on chain. The problem is, like in one of our applications, we were trying to prove basically like a massive statement, which is basically at the bounds of what is like physically computable today with Plonk, right? And if we wanted to use Plonk, we basically it would have been too expensive to prove for the statement that we were trying to prove, and so that we started looking at other proving systems that might be a little more expensive to verify on chain, but maybe still be provable. And the challenge we ran into there is, I mean, there's not infrastructure. I mean, and by infrastructure, I mean there's not even quality open source or even closed source materials available to even start experimenting with, right? So if I wanted to use a different proving system like Spartan, I have to go to the GitHub repo that was started by the professor who invented Spartan, and then try to adapt it to my needs. It's like, well, it's using this elliptic curve, but I need this curve, and let's go. You start. So, from my perspective, like the requirements are clear, but I think from the infrastructure space, I mean, there's not much, right? Like you've got Plonk, you've got Rust 16, you've got some things that are built up around there, but beyond that, it becomes a lot. Halo, there's things that are developing, but beyond that, it's a pretty new space, I guess. I mean, there's a lot of room for improvement.
And no, this is great. And Aaron, just taking this, coming down a stack, right? You have an
Yeah.
application that requires infrastructure. As Seve thinks of it, is sort of like the code, the software. That's infrastructure for a cryptographer, right? So now all of a sudden we're sitting here like, you're just going to sit there and say, wait, you're a dev tool guy that needs to run on top of something. So I'm curious from that perspective, maybe from the metal up, or like how do you reflect upon that as you're thinking? Not just does it work or can it work or easily be implemented, but can it be implemented at scale? Right. So that's what I'm really thinking about, because that's where value is going to be created when these big applications can run across large amounts of computers, deliver utility to large numbers of people. So I'm curious of your thoughts, maybe from cryptographer infrastructure to a bunch of metal running, sucking some electricity out of the wall.
I actually want to talk about what you're working on at Aligned, because I think this is very relevant here. So just to do kind of high level from the metal up, if you think about Web 2 for a minute, the metal up means I've got servers, they're running databases, they're running Apache, They're running load balancers, they're running firewalls, whatever. In zero knowledge, of course, add provers and verifiers and things like that. Now, historically, what we've done is when one server isn't fast enough, you get another server. And when two servers aren't fast enough, you get a whole data center full of them. So when you look at the metal up, I think one of the things that becomes unique and different in zero knowledge is if you think about the type of compute workload that zero knowledge is, to what you were saying, Seve, about you've got a statement that's this big and it's right at the limit of the memory of what can be done on a computer. We have the same problem in machine learning, which is what I did during my PhD. And one of the big differences between sort of an Amazon data center that runs web pages and things and what you'd consider a high performance computing facility is the minute you have kind of a single problem that multiple processors need to work on, now the processors need to talk to each other through an interconnect. In that web server example, well, you just scale out as many web servers as you want. They talk to the same backend database, but they're kind of independent. So you just run Ethernet, like even cheap gigabit Ethernet for your interconnect, and yeah, it has high latency, it's low bandwidth, it's fine. Now imagine you've got two processors and they're either working on a zero knowledge proof together or maybe training a machine learning model together. Well, they've got shared memory they have to access. And you got to be careful because if they're both accessing the same memory at the same time, then bad things kind of happen when they try to both write into the same spot. And so what happens is one processor waits for the other processor to finish with the memory, and how quickly they can talk to each other, how much latency there is, becomes far and away your limiting factor. So in zero knowledge proofs, there's a lot of Fourier transforms involved, and they use this sort of butterfly algorithm that basically turns into random memory I/O, which is the absolute worst thing possible. Because the other thing is that memory gets accessed. It's not like you have one wire to your memory chip. You usually have 128 wires or 256 or even more. So each clock that you get something from memory, you might have a latency to get down the wire, but then at least once you're done with the latency, at least you got 128 bits back or 256 or whatever. But if I'm doing random memory I/O, kind of one floating point number at a time, then if my floating point number took up 16 bits, but I got 256 back, well, I'm throwing the other 240 bits away. And so this is super inefficient. And how we've dealt with this in GPU land and also with FPGAs is they now have this high bandwidth memory that's on the same chip as the processor. And so that really, really helps. But if you've got half a terabyte or a terabyte of memory that you got to work with, then you just don't have enough memory on the chip. Now, that has been sort of the bane of high performance computing since the dawn of time. And what you do is you come up with these mathematical algorithms that say, okay, this processor can chunk away on this part of the problem for a while, that processor will do that part for a while, and then yeah, fine, they have to sync and I'll pay a cost for that, and I'll wait for them to sync, and then they'll go off and do their things, and then I'll come back. And so if you look at sort of big machine learning libraries that use like lots of GPUs, that's how they do it. I think in zero knowledge proofs with the Fourier transforms, it's a similar issue. You just need a lot of RAM. It's random access. And one of the interesting things that you're working on, Neal, is the ability to really lower the latency of the memory access, even when you're talking to multiple processors. And I do think deploying systems at scale, we're going to need specialized hardware like that, because otherwise you're just sort of into everybody wants to compute something, but everybody's waiting on just memory access. And for small proofs, that's okay, but for big ones, it's not.
Right. I like to talk about like with you're not managing memory. It's you're processing. Wait. Right. Processing. Wait. So I thought that was a really interesting to hear what you have to say. And I want to thank you guys both for doing this, because it's perfect to have the math and have a little bit of the metal and like to talk about, because these are the conversations that needs to have happen. And myself, more from the operation, business, finance side, these are really important questions, because if you come up with a brilliant solution that's just uneconomical to implement, or you result in long latency times so that the proofs can't perform to their function, you really could end up in a situation that doesn't work out. So I really want to thank you guys, Seve, Aaron, for doing this. It's a great conversation, and maybe next time we'll talk more about hardware and all these other things, or other different, those tangents that you wanted to talk about. But this was really great. So thank you guys very much. I really appreciate it. And if you want to learn more, we'll make sure that it's available, the email address, to reach out directly to Aaron and Seve and myself. So thank you very much. I'm Neal Kaufman from Aligned. Have a great day.